Hi, good evening, everyone. I'll just wait for 2 more minutes and then we can start. So, in the meantime, can you please tell if my voice is audible and is my screen visible? If you don't have a mic, you can just give a thumbs up. Okay, so we can start. Yeah, so can you please once again tell whether I'm audible or and is my screen visible? Okay, so then I will start. Good evening once again and welcome to week 4 of this problem solving session for the course on fundamentals of power electronics. So we'll just jump right ahead into the problems. In this week, you studied about basically on capacitor filter design for diode bridge rectifiers, and of course associated problems will be seen today as to how to calculate that capacitance given the ripple percentage and its applications in basic LCR circuits and so on with diodes and basic LCR circuits. So we have a total of 15 problems today, and most of them are numerical problems. We don't have much theoretical problems, so I guess 15 problems would be enough to cover the lecture. And of course, if you have any doubts, you can type in the chat box or you can unmute yourself and tell. or I will just check the chat box repeatedly. Okay. Okay. So, right. So before we go ahead, I would like to go to the last problem and we can start from over there. So just give me a second. Yeah. So look at this question. Find the conduction angle of the diode in degrees, and the circuit is something like this. This is your diode, right? So this is some inductor L, okay? And I tell that um, this V in is equal to Vm sine omega t, okay? And it is given that omega is equal to 2 pi into 50 hertz, okay? Or 50 radian per second. Okay, so this is your Vn. You have a diode over here and you have a purely inductive load. Okay, so no value is given as such. So you have a purely inductive load, and also it is given that assume IL 0 minus equal to 0. That means that initial inductor current, it means that the initial inductor current is going to be equal to 0. Right? So initial inductor current equal to 0, or it can also be told that the inductor doesn't have any stored energy prior to you turning on the circuit. Okay, so in the initial inductor current is also told to be 0. So the question is find the conduction angle of the diode. Okay, so yeah, and so let me draw Vn for our own understanding. So this is your time axis and this is your Vin. Okay, so let's say that your Vin is something like this. Okay, so this is your Vm, and of course you know that this is 360-degree, and here you have 180-degree. Okay, so before we start solving, can anybody try to answer this question in the chat box? I will just give you 2 minutes. You analyze the circuit. You have an AC source over here, voltage source, and then you have an inductive load and then a diode. Okay, so can anybody answer this question? Is it 180 degrees conduction of the diode? For how much time the diode will conduct? That means that for how much time current is going to be there, right? So the diode is forward biased or it is turned on. So can someone tell? So option A 180, option B is 360, option C 0 doesn't conduct, and option C is not enough information is given in the problem. Okay. So can anyone tell? Can anyone attempt to answer this question?
The
I will give.
options,
Yeah.
option C determinate.
Okay. So first I will correct this. Okay. So okay, you are telling that it is option D.
Third, C. Achha, it was D.
Okay. Ah, okay. So you are telling that it is D.
Yes, I
Okay.
was
So okay, good. So why do you tell that it is indeterminate? Like any rationale behind that? So what else do you need? Do you need the value of inductance, or do you need the value of Vm? Do you need the value of L? So or these are the only things that are not given in the problem. So do you need these values? If I give these values, will you be able to tell, or can it be solved numerically? What do you feel? No one is going to judge over here, so you can just attempt. You can. Okay, so Loganturai cells, it is option C, 0. So why? You can also type in the chat box. Why do you tell it will not conduct at all? This is a simple inductive load with a diode. So any um, intuition? Okay, so we will see how do we do this problem. How do we attempt this problem? First things first, let me ask, okay, let's say instead of this inductor, there was simply just a resistor. Okay, forget about the inductor for now. Okay, so let's say there was only a resistor R. Then for how much time the diode will conduct?
180 degree.
So it will conduct for 180 degrees, right? Because R is a simple passive load, right? And then if your Vn is forward bias or Vn is positive, then obviously you have the diode conducting, and during the negative cycle, the diode is reverse bias, so it cannot conduct. Okay. But more importantly, look at this question. Find the conduction angle. If it is told that find the conduction angle, it means that diode is going to carry some current, right? That is why we call it as the conduction angle. So diode has to carry some current in this direction. Okay. So the rationale we apply is, okay, so in the case of an R load, let's say this is V in and this is your current in the circuit I. Okay. So let me call it as IN as well. Or you may name it however you like. Okay. So let's say you have something like this and you tell your VN is varying like this. Okay. And so on. Right. So in the case of a purely resistive load, how will the IN look like? IN will look something like this, then 0 for the rest of the time period, then something like this, 0 for the rest of the time period, and so on. Correct? Okay, so and let us talk about the values as well. So you know that this particular value is going to be Vm, right? So what will be this value? What will be this value? This value will be simply Vm over R, right? So this will be the peak current, correct? Vm over R. Fine. So this is for R load. Okay. So any doubts over here? This is fine, right? If you have any doubts, please do tell now before we proceed ahead. Okay. So for an R load, we are seeing that during the positive half cycle, the diode will conduct, and during the negative half cycle, the diode will not conduct. So the conduction angle will be 180 degrees. Okay. So we can tell 180 degrees is the right answer for R load. Okay. So what about an L load? We need to find that out. Okay. So let me. Okay. So I will take a new slide and we can see what happens, whether it is indeterminate or doesn't conduct at all. Okay. So we'll just see what happens. Right. So this is our circuit. So you have your V in and you have your L over here. We need to find out the I. If I find out how my I is going to be, I can know what is the conduction time of the diode. If my I is going to be 0 throughout, then it is going to be something like the diode doesn't conduct at all, right? And if I'm not going to get any solution, it's going to be indeterminate. Let's see what happens. Okay. Yeah. So since I'm solving over here, if you see any mismatch or something, you are welcome to point that out. Okay, any mistake on my part or something, you are welcome to point it out. Okay, so let me write. Okay, so let's say this diode is forward biased. Okay, so let's assume this is an so let's assume this is an ideal diode. Okay, first of all, nothing has been given about the diode, so you need not worry too much. But let's say this is an ideal diode, so there is no drop. When it conducts properly like a short circuit, and when it is open, it doesn't. I mean, it can block infinite amount of voltage. An ideal switch. Okay. So with this assumption, we will try to find out what is the current in the circuit. So current is going to flow something like this, right through the inductor. What is the inductor current, or what is the relation that defines your voltage and current of an inductor? Anyone? What is the relation that defines the voltage and current of an inductor? So you have V is equal to IR. This is the voltage and current relationship in a resistive load. Correct?
So V equal to L di by dt.
Correct. So VL is equal to L into DIL by dt. And for a capacitor, you have IC equals
1
C
by
into dVc by dt. Yeah, you can just take this over here and yeah, fine. So these are the three relations that define your voltage and current relationship in your passive elements of R, L, and C. So we will do the same thing over here as well, right? So you know that VL is equal to L dIL by dt. Okay. So which means that your DIL over dt is going to be V by L, VL by L, or IL will be. So can anyone tell what will be IL? So for getting IL, what I do? For getting
integration.
IL, what we do is we integrate on both sides. Okay. Okay. So we integrated on both sides. So what will I get if I do this? Am I there over here? Are you able to listen? Okay, so first thing, conduction angle is an AC term. It's not necessarily an AC term. Conduction angle means for how much time the diode will be on. Simple. That is the question. For how much time the diode is on, and the how much for how much time the diode will be off. Okay. And Logan tells 0 to 180 degrees. It can vary between 0 to 180. Let's see how much time. Okay. Fine. So as I was telling, VL needs to be some function of time, right? So when your diode is forward biased, when D is on, right? What will be VL? VL is equal to V in, correct? That is Vm sin omega t. Okay, fine. But what are we doing over here? If I have to write this integration in proper terms, what are we doing? We are actually integrating integral DIL on one hand is equal to integral Vm sin omega t divided by L dt. Okay.
Screen is not visible.
Oh, I'm sorry. Probably it got unshared or something. My screen is not visible.
Visible, sir.
Okay, fine, thanks. Okay. So is this point clear? Just we integrated this. So integral DIL is equal to integral VL by L dt. My VL is going to be Vm sin omega t divided by L dt. Right? So this is simple, correct? Now the point is this is something like absolute integration. Okay. So integral DIL is going to give you IL. And on the other hand, you have Vm divided by L, which are constants. And then what is integral sin omega t dt? Anyone?
Minus
Integral
cos
sin
omega.
minus cos omega t and divided by omega, correct? Okay. So is this it or is there something else to this equation? See, remember over here, this integration is not bounded by any limit. Okay, we don't know what is the limit, correct? We don't know what is the limit, right? So if I know what is the limit, that will give me the conduction angle, correct? That is from whether it's from 0 to 180 or whatever it is, 180 to 360 or whatever it is. I don't know what is the limit. So it is a kind of an absolute integration. So which means that you need to add your constant of proportionality k or c or whatever you may call it. So you got it. This is the current expression. IL is equal to Vm by L into minus cos omega t by omega plus k. This is how my current will look like. Everyone agrees with this equation number 1, right? If you have any doubts, you can go ahead and tell me now. So I'll just write it over here once more. So minus Vm by omega L cos omega t plus k. Okay. Okay. This is a simple integration. Now we need to find out what is k. If I find out what is k, I will know what is the current expression. I can just get the answer. So what is k? So how do you find out the constant of proportionality in integration? Anyone? So I will go back to the question. See, you read the question carefully. Find the conduction angle of the diode in degrees, and it is the circuit is given, and it is also given that V in is Vm sin omega t, and you have a purely inductive load. Assume initial inductor current is equal to 0. That is, assume IL of 0 minus equal to 0. Okay, right? That means at t equal to 0, my IL is 0. Correct? So this is what we can infer from the initial condition that has been provided. Okay, initially the circuit was uncharged. Fine. So with this assumption, now we will go back. So now can we find out what is K? We know that from initial conditions at t equal to 0, my IL equal to 0. Correct? So you just substitute it over here and you get the answer. Correct? So what happens? IL equal to 0 is equal to minus Vm by omega L cos omega t. T is 0, so cos 0, right? Cos 0 plus k. Oh my god. Okay. Which means that k is equal to minus Vm by omega L. Okay. So any doubts over here? Is this fine? So you get what is your k, right? So k is equal to minus Vm by omega L. Therefore, you see that your IL is going to be how much? Your IL will be something like minus Vm by omega L cos omega t minus Vm by omega L. Correct? So are you guys able to follow so far?
So K will be positive.
K will be, okay, sorry. So there is a sign mistake. Correct. Yeah, K will be positive. Okay. So thanks for that. So IL will be what? Our IL will be Vm by omega L into 1 minus cos omega t, right? Is this fine till this point? If you have any doubts, please write in the chat box. Okay, so we just substituted the initial conditions. We found out what is the constant of proportionality or what is K. Now I have what is my IL, correct? So with this information, I can go ahead and plot how my K will look like, how my IL will look like. Then if I know what is IL, I know the conduction angle of the diode, correct? So okay. Um, okay. So this is V in and this is IL. So your Vn is varying something like this. Okay. So how is Vn varying? Vn is equal to Vm sine omega t. And what about our IL? IL is equal to Vm by omega L into 1 minus cos omega t. Correct? So how will this vary? So this was Vm. Anyone? How will this vary? How will IL look like? Okay. So from this itself you substitute at t equal to 0. Our IL is 0, right? At t equal to 0, cos 0 is 1. So 1 minus 1 is 0. Okay. And let's say so let's say omega t is equal to 180 degrees. So what will be omega t at omega t equal to 180 degree? What is cos 180? Cos 180 is going to be minus 1. So 1 minus of minus 1 is 2. So it will be IL will be 2 Vm by omega L. And at omega t equal to 360, IL is going to be what? IL will again be 0. Okay. So IL is 0 here. IL is 0 here. And at omega t equal to 180, your IL is going to be 2 Vm by omega L, right? So you can of course plot in the middle what it would look like, correct? So let's say omega t is equal to 90 degrees, correct? So what is cos 90? Cos 90 is 0, okay? So your IL will be equal to Vm by omega L. Similarly, at omega t equal to 270 as well, it will, you can see what it will be. At omega t equal to 270 also, cos 270 is again 0. So IL will again be equal to Vm by omega L. So you see at omega t equal to 90 and omega t equal to 270, you are having Vm by omega L. So now you can join the dots and lo and behold, this is how your inductor current will look like. Got it? So any doubts over here in the plotting of inductor current? Okay. So Divakar, IL equal to Vm by omega L 1 minus cos omega t. How did you get? See, we just derived it, right? So I'll just go through the derivation again. So you know that VL equal to L di dt, right? And what you do is you want to find out the current expression, IL expression. So how did we get the IL expression? By integrating this particular equation, you get IL equal to Vm by omega L into minus cos omega t plus K. This is a constant of proportionality which you generally add with any absolute integration wherein the limits are unknown. Okay, so you got what is IL, and from the given question, that assume initial condition to be zero. That means that at t equal to zero, your IL is zero. Initial inductor current is zero. Okay, so substitute this particular point in the above expression in this equation. Okay, and you get what is K. Okay, so once you get what is K, you plug it back in that equation and you will get the expression IL is equal to Vm by omega L into 1 minus cos omega t. Okay, okay, so with IL known, I just plotted how IL would vary with time with omega t. Okay, so did you guys understand this? How we derived? Okay, good. So now that we have got this, now can you tell what is the right answer for this question? Find the conduction angle of the diode in degrees.
Continuously conducts 360
Exactly.
degrees.
So the answer is 360 degrees. Okay. So people generally think along lines of either 180 degree because it's a diode, or doesn't conduct at all, or indeterminate. But the right answer is it continuously conducts. Or intuitively, you can tell something like it's an inductive load. So a pure inductor always opposes change in current. Okay, it doesn't want current to go zero and stay at zero at all. Okay, so that is why you will see that during the positive half cycle, the inductor charges, and during the negative half cycle, it discharges. Okay. Or you think of, so this is the derivative part. Okay, so this is the derivative part. Now we will try to get the same answer with simple intuition. So if you want the exact values of these, you of course need to derive, only then you will get this is 2 Vm by omega L, this is the peak value. Okay, so to get the peak value at all, you need to derive the equation, no doubt. But how do you get the answer intuitively? That is, without this much math, can I get the answer intuitively? Okay, can I get, or can I just understand how the curve would look like? Correct. So we will just draw the Vm expression, V in expression again. So we told that our V in is something like this. Okay. So how my IL would look like? This is your V in. Okay. So now the point is, see, this V in is appearing across the inductor. You know, simple, right? You know that V is equal to L di by dt. Okay, that is, or you can write that voltage across an inductor is proportional to di by dt. Okay, so it means that, so the voltage that you see over here, it is actually the derivative of the current. Correct. So voltage that you see over here is the derivative of the current, or conversely, as we derived earlier, you can tell that I is proportional to integral of the voltage. Correct? Is it fine? I is proportional to integral of the voltage. Okay. So now we will come back. So you have V is proportional to dA by dt, or I is proportional to integral of the voltage. So you see during the positive half cycle. So during the positive half cycle, you see that your voltage is positive, right? So if your voltage is positive, you are integrating a positive area. So what will happen? Therefore, current increases. Okay, current will increase. So it's going to be something like this during the entire positive half cycle. Since your area is positive, it's a pure inductive load. It's applicable only for pure inductive load, of course. So since your voltage is positive, your area is positive, that is your integral is positive. So current is going to be directly proportional, right? So it's directly proportional to that, or your current is going to increase during this interval. And what will happen during the negative half cycle? During the negative half cycle, you know, voltage is negative. Therefore, what will happen to current? Current decreases. So current will go something like this, and this is going to continue, which means that my inductor is going to conduct during the entire 360 degrees. Simple, right? This is a simple approach because it was only an MCQ question. But if you had to derive, of course, you can derive. Derivation is also not that tough, but you can just use your logic and tell V is equal to L di dt. So I is proportional to the integral of voltage. If my area is positive, current increases. If my area is negative, current decreases. Right? Okay. So this particular question, did you guys understand the approach that we followed for the for solving this problem? Yeah. So okay. Now we will go and start off from the beginning. Okay. So now there is a slight modification to the circuit. Earlier we just saw an voltage source and then a diode and inductor. Now it is said that a diode is connected in series with an LC load as shown in figure, with the capacitor having an initial voltage of 100 volts. So across this capacitor you have an initial voltage of 100 volts. VC0 is 100. Okay, capacitance is 10 microfarad and inductance is 40 microhenry. Okay, if the switch is closed at t equal to 0, determine the conduction time of the diode. Okay, so now remember that it's not an L circuit, it's now an LC circuit. Okay, so how do we solve this? Okay, so before we go into the numbers, can anyone tell how to solve this question? It's just an LC circuit. Okay, so before we do solve this question, we can try to get the answer intuitively. Okay, we will try to get the answer intuitively. Okay, so if you have an LC circuit, what happens? So let's say I have some circuit and I have let's say a voltage source. There is a voltage source and L and C are there. Okay. So what will happen? So how will current flow, or what do you expect them? What do you expect to happen? You just have a source and then L and C. Anyone? Any idea? You have a voltage source, DC voltage source, let's say, and then you have L and then a C. Okay, so are you guys familiar with the concept of resonance? Something called resonance. You can just give a thumbs up, or I think all of you might have studied resonance in your first year circuit theory or networks analysis or so, right? So now you forget about power electronics. Power electronics is nothing but some switches and R, L, and C. That's it. Nothing too complicated about that. So it's just an extension of your first year circuits and systems. I mean, first year circuit theory. So we go back to the circuit. Now you try to tell me you have an L and a C. You forget about the diode right now. You have an L and a C, and it is also told that the capacitor has an initial voltage of 100 volts. Okay. So you can assume the initial voltage of the capacitor is a DC voltage source, and then you have an L and C connected, correct? So now are you able to correlate it with the resonance that you learned previously? You might have learned that during resonance in a simple LC circuit, let's say have something like this, you might have learned that the resonating frequency, right? So let's say I want to see the voltage across this capacitor, VC, okay? Or I want to find out what is the current. So you will see that the value of VC will not be constant, correct? So it will have some kind of resonance. Okay, it will have some kind of oscillation. Okay, and what will be the frequency of that oscillation? Frequency will be equal to anyone?
1 by
1,
2 pi root LC.
1 by 2 pi root LC. Okay, so this will be the frequency of your capacitor voltage and your inductor current. Okay, we call inductor current IL and capacitor voltage VC as the state variables in the circuit. Okay, IL. So the frequency of both of these quantities is going to be 1 by 2 pi root LC. Okay, so your inductor current, if you actually let me take another slide for example. Okay, so we just established that in an LC circuit, right? You have something called resonance and your VC and IL. Both of these, which are known as state variables, are going to have a resonating frequency of 1 by 2 pi root over LC, which means that your VC will vary something like this. Okay, and your IL is also going to vary something like this. Okay, and what will be this T? The time period. Time period is equal to 1 by frequency, or the time period will simply be 2 pi root LC. Correct? So this will be your IL. This will be VC. Okay. Okay. So is this understood? Now that we have this, we will go back to the rest of the circuit. So ideally, if you just have a voltage source, capacitor and inductor, you expect the frequency to be 1 by 2 pi root LC, or the conduction time to be 2 pi root LC. Now in the question they have given that there is a diode. Okay. So you know that diode will conduct for how much time? Diode cannot conduct negative portion of the current. Correct? So diode can conduct only this particular portion. Correct? Yeah. So diode can conduct only this particular portion of the current. Obviously, diode cannot take in negative current. So if you include the diode in the circuit, how will the current look like? The current will look something like this, and then it will be zero. Diode doesn't allow any current during the rest of the period. Then again it will increase. Got it? So now you tell me, what is the conduction time of the diode? Anyone? What is this period? This is the conduction time of the diode, right? This is T is equal to 2 pi root LC. So what is this period? Conduction time TC. Anyone?
Pi root LC.
Right. So this will simply be pi root LC. Okay. Now we just substitute these values and find out pi into root over 10 micro into 40 micro. So pi into root over 10 micro into 40 micro, or pi into root over 400 micro. Correct? So root over 400 is 20. So it's going to be 20 pi into 10 power. Okay, so we'll just keep aside micro for right now. Okay, so it will be 20 pi microsecond. So 20 into 3.14. So 23 are 60. So something around 60, right? So 60, around 60 microseconds or so we should get. So how much does it? Yeah, so you have the answer 62.8 microseconds. Are you able to understand? Simple resonance. Okay. Any doubts, anyone so far? Yeah. So again, going back, you just see there is the capacitor has some initial voltage, 100 volts. So it's like a DC source, and then you have an L and C. So if you know that the resonating frequency is going to be 1 by 2 pi root LC. However, there is a diode over here which cannot conduct the negative portion of your inductor current. Okay, this portion the diode cannot take in. So diode will conduct only during the positive portion of your inductor current. So what is that period? It will be half the time period, right? So your total time period is 2 pi root LC. So half the time period is pi root LC. Okay, so yeah, fine. Okay, so just a second, I will just check the time. Okay, it's 6:49. So as usual, we will see some questions by solving and some questions we can just see using the solutions. Okay. Okay. A single phase diode bridge rectifier supplies a highly inductive load of 20 amperes. Okay. What is the value of the fundamental component of the input current in amperes? Okay. So first, you draw the circuit for our own understanding. So what they are telling us, you have a DBR, single phase diode bridge rectifier. So you have something like this, and it supplies a highly inductive load of 20 amperes. So I can almost tell that over here I have a current source of 20 amperes because it's highly inductive. So you can assume that it's a current source. So it is a 20 ampere current source. Okay. What is the peak value of fundamental component of input current? So this is your V in. Okay. And let's say this is your I in. So first things first, we need to find out what is I in. And based on that, we will see what is the peak value of the current. Okay. So, just a second. So, how do you think I in will look like? So, what will be the shape of I in? Anyone? So, V in is a pure sinusoidal voltage, and they have told that the output current is almost constant. It's a highly inductive load of 20 amperes, which means that it's almost constant. It's like a current source, and it is sinking in 20 amperes. Okay. So, what will be the shape of I in? Anyone? Any attempts? Will it be sinusoidal? Will it be? Will it have only for 180 degrees, or will it be rectified sinusoid, or will it be a square wave or triangular? What do you feel? Any intuition? Anyone?
Rectified sinusoid.
Why do you think it will be rectified sinusoidal?
Like in the forward bias, like D1 and D2 is conducting, and in the negative half cycle, D3 and D4 will conduct.
Correct. So you know that D1 and let's say this is D2, D3 and D4. So you know that during D1 and D2, I mean during positive half cycle, D1 and D2 are going to conduct when Vn is positive. When Vn is negative, D3 and D4 are going to conduct. We don't know what is In. We don't know how In will look like. Now the point is, see, over here there is a constant current of 20 amperes that is going. Okay. Now let me draw the circuit. Okay, during both intervals, then we will get an idea as to how in will look like. Because only if you know how in will look like, we can put whatever Fourier series expansion they are asking us to put. Correct. So we first need to know how in will look like before we jump into any conclusion. Right. So
IN is
see.
a square wave.
Yeah, so why do you feel so?
Sir, in output we get a constant current of 20 amperes.
Correct.
Is why I think it's a square wave.
Correct. So when D1 and D2 are on, that is this and this are on, how will the circuit look like? The circuit will look like something like this. So it goes over here and then this is on. So this is something like this. So it is already on. I am bypassing it something like this. And then it goes to the load. The load is something like this. And then it comes back through D2. D2 is anyway it's shorted. Let's assume these are all ideal diodes. So you get something like this. Okay. So I will erase this off. I will erase this off. Yes. So this is the circuit you end up with. And over here you have your IN. So what is IN when D1 and D2 are on? IN is equal to 20 amperes. When D1 and D2 are on, IN is equal to 20 amperes. When what is IN when D3 and D4 are on? So again, you have your so when D3 and D4 are on, so you come over here and then this diode is on actually. So you have something like this and then you have something like this, correct? Sorry. So you have something like this, okay? And then you have something like this. So here this is positive and here this is positive. So if you see what is IN conventional direction is something like this is what we have considered. So you can understand that during when D3 and D4 are on, your IN is equal to minus 20 amperes. So you see in both cases that IN is 20 amperes fixed or IN is minus 20 amperes fixed. So now you draw the waveform of IN.
Yes, a square
So,
wave.
so this is your sinusoidal, correct. So this is your sinusoidal voltage. Therefore, your IN will be 20 amperes during the positive half cycle and minus 20 amperes during the negative half cycle and so on. Okay. So what you get is actually a proper square wave. Okay. So what you get is a proper square wave. Okay. So this is how your IN will look like. So your square wave has a peak of 20 amperes and what will be the RMS of a square wave? RMS is simply equal to 20 amperes, correct? So RMS is equal to 20 amperes, obviously in a square wave. But however, look at the question. What is the peak value of fundamental component of input current? Now the point is you got a square wave. Okay, so you have got a square wave, but they are asking the peak value of your fundamental component. Okay, so they are asking the peak value for fundamental component. So how do you find that out? You can do so using Fourier series expansion, correct? So they have given that in the hint as well, right? So if you do Fourier series expansion, so what will you end up with? You will end up with the peak value being peak value of fundamental will be what? So the idea is you get 4 in by n pi, right? This is your peak value, correct? If you remember your Fourier series, you get 4v by n pi or 4I by n pi. In our case, it is 4I by n pi, correct? So we are dealing with fundamental. So since we are dealing, okay, so here you have the answer anyway, but yeah, since you are dealing with fundamental, n is equal to 1. So your peak value will be how much? 4 into 20 by n is equal to 1. So 4 into 20 by pi or that is equal to 80 by pi. Okay, so we just need to find out. So what will be 80 by pi? So it may be somewhere around 80 by 3.14. Correct. So how much does it turn out?
95.45.
Right. So it will turn out to be something like this. Did you understand how we did this? We have a single phase average rectifier and they have given that it's a highly inductive. So you have a constant current source of 20 amperes at the load. So you just go back from the load side towards the source side, you can get what is I in. When D1 and D2 are on, I in is 20 straight, and D3, D4 are on, I in is minus 20. This is also straight. So you see that I in is going to be a proper square wave, correct, with an amplitude of 20 amperes. Now they have asked what is the peak value of fundamental current. Okay, peak value of fundamental current. If they don't ask, if they ask for RMS value, you just need to do by root 2, correct? 4 in by n pi by root 2. So this is for fundamental. If they ask third harmonic, sixth, fifth or seventh or ninth, you can do it, right? By just substituting for the particular value of n. Okay, so this is a peak value. And if they ask RMS, as I told, you need to do by root 2. Okay, yeah. So yeah, so 25.45 amps. Okay, so any doubts so far here? So the peak inverse voltage of the diodes in a full bridge rectifier is 200 volts. Okay, so we are just in third question. What is the time? Okay, it's 7. So the what is the peak inverse voltage of diodes in full wave center tap rectifier? So I guess you would have studied about this in the lecture slides itself about a full wave center tap rectifier. You know that in a center tap rectifier, right? So I will just tell very briefly, correct? So what you are doing is something like you might have also studied this something like this in transformers as well. So what you are doing is something like you are tapping it in the middle, correct? So you get a voltage over here and you get the same voltage over here as well. Okay. So what the diodes will block, peak inverse voltage is the blocking voltage of the diodes. It's going to be 2 times whatever is the voltage you get for full bridge rectifier. So 2 times 200. So you will be getting 400 volts. Simple. It's a center tap rectifier, so it will be double the voltage, right? Okay. It will be double of full bridge configuration. So you would have studied the topology in the lectures. I'm not going into that. We can go ahead with the next question. Okay, so this is another simple question. For a 3-phase 60 hertz 110 volts input supply, the output ripple frequency is dash. In output ripple frequency in 3-phase full wave rectifier. So any answers, please? Anyone? You can type in the chat box as well. So for what load, I in will be sine wave. So for RLC loads, you can have sine waves. Okay. If your load is an RLC, right? We were talking about resonance and all. So if your load is an LC load or an RLC load, you can have sine wave. There are converters, power converters, which allow you to have a sinusoidal input current irrespective of the load. They are called power factor correction converters. You will read about it probably in masters or something, but yes, you can have sinusoidal input current for you can have sinusoidal input current as well. So why Bn coefficient in question 2? So the reason being that it is half wave symmetric, right? So if you have it being half wave symmetric, you obviously need not take in An, and of course, since it is in the input side or it's an AC quantity, there will not be any average value. So A naught is 0, An is 0, so you have only Bn. that too for n equal to 1, 3, 5, 7 and so on. Okay, so that is why Bn coefficient is only taken. Okay, and yeah. So any answers for a three-phase full wave rectifier? Okay, so you would have studied about the topology itself. Sorry, it should not come. Okay, so what is the topology? You have something like this, correct? So this is connected to the load, and you have, let's say all of this is a balanced three-phase supply. So you have something like this. So output ripple frequency will be how much? It is based on for what time or what time interval each of the pairs of diodes are conducting. You know that for between 0 to 60 hertz, one will conduct and one pair will conduct, then 60 to 120, 120 to 180 and so on, right? So based on this itself, you can guess that the output ripple frequency will be 6 times your fundamental frequency. So 6 times 60, or it is going to be 360 hertz. Again, this is something you would have studied in the lecture as well. So I'm not going to linger on this for longer time. Okay. Yeah, output ripple frequency is 6 times the input frequency for three-phase full wave rectifier. Okay. So a rare theoretical question. What are the advantages of a diode-based rectifier with filter capacitor? So you have a DBR. With the filter capacitor. Okay, so some advantages are, of course, you have a high volumetric efficiency. Okay, and okay, so before we go ahead, what do you think will be the power factor of the circuit? This is covered in the lecture slides as well. What is the power factor of a DBR with a capacitive load? What is the power factor? How do you think the THD will look like? What will be the THD? Total harmonic distortion and all.
Excuse me, sir.
Sorry?
Sir, where it is shared? You have said it is shared.
Oh, you're not able to see my screen? Just a second.
It's visible, sir.
Okay. Yeah, so we were just seeing this problem. Okay, so in the interest of time, I'm just going ahead because it's just a theoretical problem. So it will have a high volumetric efficiency. Obviously, low power factor is not an advantage, and it does have low component count because you just have 4 diodes and it can be integrated in a single package. You just need a capacitor and a resistor. Okay, so it has low component count, and having high initial current is definitely not an advantage. Okay, so high initial current is required to charge up the capacitor, right? So it will take up a huge current because I is equal to C dV dt. Let's say your capacitor voltage needs to go to 400 volts, and initially capacitor voltage is 0. So it tries to go to 400 volts immediately, which means that it will take in a huge current. So huge initial current. Okay, so that's also not an advantage, obviously. So yeah. Okay, so with this only we have a few problems coming up. Consider the diode bridge rectifier. if 230 volt 50 hertz AC input is given to the rectifier circuit, where input voltage can vary in the range of plus or minus 10 volt, calculate the peak inverse voltage rating for the diode. So how do you think we should calculate? 230 volts is the input voltage. Okay. So see, one thumb rule is, if they only give something like 230 volt, is this RMS value or is this peak value?
RMS value.
Okay, so it's an RMS value. So only if they specify something like 230 sine omega t, then 230 becomes peak, or else if they just give the number, it means it is just an RMS value. Okay, so the point is Vn will be something equivalent to 230 root 2 sine omega t. Okay, so input voltage can vary in the range of plus or minus 10 volt. So 230 root 2 plus or minus 10%. Okay, it can be plus 230 root 2 plus or minus 10%. Calculate the peak inverse voltage rating for the diode. Okay, so generally we tell the peak inverse voltage rating to be, okay, it's not, but anyway, so we tell the peak inverse voltage rating to be Vm, right? We tell the peak inverse voltage is Vm for this diode rectifier. However, here it is told that it can vary plus or minus 10 volts. So your diode needs to be rated for the extreme condition, right? So your peak inverse voltage in this case, it will actually be Vm plus 0.1 Vm, right? So 10%, okay? Or 1.1 Vm. So 1.1 into 230 root 2. Anyone?
So 357.79.
Yeah. So 357.79. Okay. So this is the peak inverse voltage. Just we considered this plus or minus 10% and we just got it. So again, a simple problem. We will just go ahead. Yeah, 357. Okay. So previously we saw one problem, right? About um, a diode circuit with an inductor and an AC voltage source. So this is something similar to that. A single phase diode bridge rectifier is connected to a purely inductive load. Then find the conduction angle of the diode D1. So for how much time D1 will conduct? That is the question. So before we go ahead, just give me a break for 2 minutes. I'll just have some water and come back. So meanwhile, you please try to think about this. That is, you just have a diode bridge rectifier, okay, and it is connected to a purely inductive load. Okay, instead of a single diode, you have a diode bridge rectifier, AC source. It's connected to an inductive load. For how much time diode D1 will conduct? That is the question. For how much time D1 will conduct? It will be 0, 2 pi, or pi by 2. So please think about it. I'll just come back. Yeah, so any answers to this question? Find the conduction angle of the diode. So any guesses? How much should it be? You don't need to think much. Think from the inductor side, okay? Okay. So during positive half cycle, what will happen? So your diode D1 is on, so it flows through the D4 and back. So this is what happens during the positive half cycle. During negative half cycle, you know that inductors opposes any change in current. So your current direction has to be like this through the inductor. So of course, it will come like this, correct? Till this point it has come. It cannot go through D4, reason being that your Vn is right now, polarity is over here. So D4 is reverse biased. So it will go through, it will go only through D2, right? So it will go through D2, then how will it go? So it will go through D2 and then through D3 and back. Okay, so D1 is conducting for how much time? Only during the pi interval of the total 2 pi period. Okay, so D1 conducts for 180 degrees or pi. Okay, simple, right? Just track from the inductor side, you will get the answer. Yeah. Okay, so if in the diode bridge rectifier shown in figure, if current I is equal to 10 plus 0.2 sine omega t and the average value of load current is 10 ampere, then what will be the approximate value of the capacitor current marked in figure? Very simple question. So anyone, what is IC? Hello, am I audible? Yes. Yeah, yeah, it is 180. So anyone for this answer? Very simple question. So in this circuit, what is IC? Your I is given, your average value of load current I naught is also given. So what is IC? What is IC? IC is equal to I minus I naught. So 10 minus 0.2 sine omega t. So it will just be 0.2. 0.2 sine omega t, right? Or in other words, so this is one way, of course, by KCL. Or in other words, you always know that capacitor cannot take any average value of current under steady state, right? Because if it takes a fixed current, the capacitor voltage will just go on increasing, right? Because I is equal to C dV dt or V is equal to integral I. So if you give a fixed DC current, it will just go on, the capacitor voltage will go on rising. So that will never happen during steady state. So obviously the capacitor current is always a ripple. Okay, it will always be an AC quantity. The capacitor current is always an AC quantity. Okay. So that is why you can also tell that it will simply be 0.2 sine omega t. Okay. Again, a very simple question. Yeah. So we will go ahead with the next. I'll just check the chat box once. Okay. So the output voltage waveform for the circuit shown in figure 8 is shown in figure. So what was the figure in figure 8? Yeah. So this is just a DBR, direct bridge rectifier with a capacitive filter and a resistive load. So if the value of capacitor is 1.5 millifarad, Vm1 is 200 volt, Vm2 is 190 volts. Find the energy lost by the capacitor during the discharge period in joules. Okay. So you know that, sorry. So you know that this particular period, right? This particular period is your charging period, right? And this period is your discharging period. So he is asking what is the energy lost by the capacitor during discharge period. Okay. So C is given and VM1 and VM2 both of them are given. Okay. VM1, VM2 all of these are given. So anyone, any guesses? How do you find out the energy lost by the capacitor during this discharge period?
Half
So
CV
what is
square.
the correct? So half CV square. My question is, what will be the energy lost? So VM1 is given, VM2 is given. So what do you need to find? You need to find the energy at this point, find out the energy at this point and subtract both of them, correct? So it will be half C V1 square minus half C V2 square. Okay. So half into C into V1 square minus V2 square. So 200 square minus 190 square. Correct? What is the answer? Half into 1.5 milli into 200 plus 190 is 390 into minus 190 is just 10. So 15 into 390 into. So what is the answer you are getting? 15 into 0.39 by 2. Yeah. So around 2.925 joules. So this is the energy that is lost. Okay. During the discharge period, there is the energy that is lost. Okay. And you of course know the profile, right? Why? I'm sorry. Yeah. So the reason when your capacitor voltage is below your AC input voltage, obviously the capacitor will charge up, correct? And once your AC input voltage goes less than the capacitor voltage, the capacitor will slowly discharge into the load. Okay, until your AC input voltage becomes higher than your capacitor voltage. Okay. Yeah. I think this has been taught in the lecture as well. If Vn is more than your capacitor voltage, then capacitor charges up, charging period. If Vn less than your Vc, then capacitor discharges onto the load. Discharges to the load. So that is why you see that the discharging profile is okay. Over here it's a straight line, but it will actually be an RC discharge, right? Because you have a C and it will discharge into R, correct? During the discharging period. Okay, fine. Again, a diode circuit. What is the correct average load voltage across the AB terminal shown in figure below? Consider that the diode is ideal. So very simple, right? So can anyone tell directly? V in is Vm sin omega t. So when Vn is positive, diode
Minus
is
Vm by pi.
minus Vm by pi. So we will just so when Vn is positive, diode is reverse biased. So obviously, and when Vn is negative, diode is forward bias. So what will be VAB during that time? VAB during that time will be equal to just directly V in, right? Okay. And during this time it will be equal to 0. So if you plot it, you will be getting when V in is positive, diode is reverse bias, therefore VAB is 0. And when V in is negative, the diode is forward biased and VAB equal to V in, right? You will get something like this. Okay. So we just need to find out the average value, or you need to find out the average value means you need to find out the area. Okay. Yeah. So this is the output voltage you expect, that is V0 or VAB. So you just need to find out the area, right? So area will be what? Area is basically the average value, or area is basically 1 by T integral 0 to T f of t dt. Okay, your f of t is actually Vm sine omega t. So you just substitute that over here. And what is the time? Okay, so I should not write 0 to t. So it should be t1 to t2. What is the time? So t1 is pi between this point to this point. Correct? So you just substitute that and find out the area. You will get, yeah, as you told, right, it is minus V by pi. It is minus Vm by pi. Did you understand this question? Any doubts? I did not solve it straight away, but I think this is pretty straightforward. Correct? You just need to find out the area and divide it by the total time period. That will give you the average. Okay. Yeah. So always you remember one thing. If they find out the average, if they ask for the average load voltage or RMS load voltage, just go back to definition. Okay. So you know that your, oh my god, you know that your average voltage average value of any quantity is given by integral 1 by t integral t1 to t2 f of t dt, or area by time. What is RMS? RMS is root mean square. So root of mean square. So root over 1 by t integral t1 to t2. Root means square, right? So f square of t dt. So this is the definition of RMS. So you just remember these definitions, and for any function you should be able to find out. Okay. So over here this has been asked for this diode circuit. So we just substituted it and we got, right. We just find out the area. You get Vm by pi. Correct. It is minus Vm by pi. Okay. Any doubts so far? Okay. So the capacitor filter is added across the load side in the figure of question 10. Calculate the average current through the capacitor filter. Average current under steady state, if Vm is this, C is 2 millifarad, Vm is 325.26, R is 100. Okay, so what they are doing is, in this circuit, they are adding a capacitor filter across the load. Okay, so how will the circuit look like right now? The circuit is going to be something like, so they have added a capacitor across the load. Okay. Okay. So intuitively, by seeing this circuit itself, can you tell me what is the average capacitor current IC? So average, since it is average, I am writing it as capital I. So what will be IC, average capacitor current? assume that it's an ideal diode. Is it possible to tell, first of all, what is the average capacitor current? Just by seeing the circuit and seeing whatever is given in the question, calculate the average current through the capacitor under steady state. So, is it possible to tell the answer? Just think for a minute. See the circuit, and you of course know that some current is going to come. Let's say, okay, so diode is facing this side. So let's say the current will come like this, and current will split like this and by this way. So what is the average capacitor current? That is a question. Under steady state, not under transient state. Under steady state, what will be the capacitor current?
The steady state, it would be open circuited.
Correct. So what will be the capacitor current? It will be 0, right? Correct answer. So one intuition is under steady state, capacitor acts as open circuit. Okay, and inductor, if it is given, it acts as a short circuit. So if you tell the capacitor is open under steady state, your current is obviously going to be 0, right? Or by KCL, you know that the current, the total current over here, let's say it is IT, it is going to split between the resistive branch and the capacitive branch. Okay, so what will be the resistive current? It will be V by R. And what will be the capacitor current? It will be some V by omega C. Correct? Sorry, it will be, so you know that XC is equal to 1 by omega C. So I is equal to V by XC or V into omega C. So it will be V into omega C. Under steady state, omega is 0. Omega equal to 0 at steady state. Therefore, so you know that IC will also be 0 because V into omega C, right? Under steady state, omega is 0. Therefore, your IC component of current will also be equal to 0 at steady state. Correct? Okay. So, yeah. So, the current will always be a ripple AC current. Capacitor will always take in only AC current during the steady state. It cannot take DC current. Okay. So, average current will always remain as 0. Okay. Yeah. So, let me check the. Yeah, it is 0, correct. So for the circuit and waveform shown here, yeah, again it's a similar circuit. The output has a voltage ripple of 5% of input peak voltage. Okay. Assume the switches to be ideal. Calculate the discharging period for the capacitor in degrees. See, what they have given is, let's say, yeah. So let's say this is Vm. They are telling that this particular point is 5% lesser, correct? The voltage ripple is 5% of peak input. So this point will be 5% lesser, or it will be 0.95 times Vm, correct? So the ripple is between 0.95 Vm to Vm, 0.95 Vm to Vm, and so on. Okay. So calculate the discharging period for the capacitor. They are asking what is this particular period. Okay. So you have alpha. This is alpha. Then alpha to pi by 2 is your charging period. Then pi by 2 to again pi by 2 to pi plus alpha is your discharging period. So what is a discharging period? This period, from the figure itself, it is evident that the discharging period is between pi plus alpha to pi by 2, right? So it is going to be pi by 2 plus alpha. This is the discharging period, correct? So discharging period will be pi by 2 plus alpha. So we just need to find out what is this alpha, and yes, that's it. Our answer will be done. Okay. So we will take the refuge of what is given over here, right? So it is given that at omega t equal to alpha, V naught is equal to 0.95 times Vm. Correct? This is a point, right? 5% triple is given. So we know that at omega t equal to alpha, V naught is equal to 0.95 Vm. Okay? Omega t equal to alpha, V naught is equal to 0.95 times Vm. Or you know that Vm sine omega t is equal to 0.95 Vm. So Vm and Vm will get cancelled. You can find out what is omega t. Your omega t is equal to alpha during this time. Therefore, sine alpha is equal to 0.95. Therefore, alpha is sine inverse 0.95. So what is sine inverse 0.95? Anyone? Sine inverse.
71.80.
Correct. So 71.8 degrees. Okay. So this is your alpha. So once you know what is alpha, what is your discharging period now? Pi by 2 is 90 degree and 71.8. So what is that? 90 plus 71.8, 161.8 degrees. This is your discharging period. Simple, right? From the given condition only, they gave that the ripple is 5%. So this is point, the minimum point is 0.95 Vm. That occurs at some value alpha. So let's find out that particular angle, that is alpha is known. Now that alpha is known, discharging period is between pi by 2 to pi plus alpha, right? So see, in this particular question, they have named these as alpha, pi by 2, pi plus alpha for our convenience. But intuitively also, you know that peak will occur at pi by 2. So prior to that, you have your alpha. So this particular point will be pi plus alpha, correct? So even if these alpha or angle values are not given, you should know to calculate. Okay. Yeah. So the answer is alpha is 71.8. So discharging period is 161.8. Okay. Right. Again, so it is the same question. For the circuit and waveform shown in figure 12, compute the capacitance for a ripple voltage of 5% of peak value, same of the sinusoidal input voltage with 50 Hz frequency. So now the question is, calculate what is C. Okay, so can anybody tell a way to calculate this before I tell the way? From the given, you see the question, you see the circuit diagrams given, you see the values given. So can anyone formulate a way to calculate the capacitor ripple current or capacitance? You analyze what is going on in the capacitor. When the capacitor is charging, what is the equivalent circuit? And when the capacitor is discharging, what is the equivalent circuit? If you know that, you get the answer. So any hinges, any hunches? How do I find out the value of capacitance over here? Hint is you look at how the capacitor charges and how the capacitance discharges. From that itself, you can tell easily. I don't want the correct answer, just the approach. If you can tell, it will be great. Try to think a little. I will just give 1 minute. Okay, so let me turn on my camera once again. Right. So as I was telling you, try to analyze what happens in the capacitor, right? So during the charging period, right? During this period, let's say during this period, then this diode is on, this diode is on. So your capacitor charges something like this, correct? But this is a bit complicated, right? You have diodes coming into the picture, not directly possible to calculate the capacitance, but you consider the discharging period, right? What happens in the discharging period? The capacitor just discharges to the load. It is a simple resistor. Okay. So what is the current through the resistor?
Not
IR
by
is
hour.
equal to, correct. So it will be V naught by R. IR will be V naught by R. So you know that when the capacitor is discharging, the capacitor current IC is equal to what? V naught by R, correct? During this period, during this particular period, you know that the capacitor current is V naught by R. Okay, correct? And so this is one, or capacitor's current can also, what is the relation between capacitor voltage and current?
C
I
dV
is
by
equal
dt.
to C into dV by dt. Okay, now can you tell? See, IC is equal to V naught by R, that is 1, and C into dV by dt. You know that during this period, your V naught is falling from Vm to 0.95 Vm, correct? Your voltage is falling from Vm to 0.95 Vm. So that is your dV. And you know what is the discharging period? We just found out what is the discharging period. So you know dt, you know dV, and you need to find out C, correct? And R is also given as 200 volts. So from this, can't you find out what is C? Did you get it, the approach? So yeah, so during the discharging period, you know that capacitance will discharge only through the load resistor. So the load current is equal to capacitor current, which is V naught by R. You also know that the fundamental relation that defines capacitor voltage and current is going to be C dV by dt. Okay, you know that the voltage falls from Vm to 0.95 Vm, 5% ripple, right? So Vm to 0.95 Vm. So you know dV. We just found out the discharge period in the previous question, right? Discharge period was how much? 161.8 degrees. You convert it into time, omega t, right? You convert it into time. You know what is dt. So dV is known, dt is known, and R is given as 200 volts. You know what is V naught. You can get what is C, right? Did you understand? Anyone has any doubt as to how we are approaching this problem? Okay, so just try to solve it. Right. So what is dV? dV is, it is going from Vm to 0.95 Vm, right? So Vm to 0.95 Vm. So dV is simply 0.05 Vm, or what is Vm? Vm was given in the previous question. Okay, so it was not given exactly. So let that be an unknown for now. Or we can assume 230 volts. Okay. And what is dt? dt, we calculated the discharge period as some 161.8 degrees, right? Or in time, what will, so this is omega t. Omega t is equal to 161.8. So what is t? 161.8 by omega. Omega is 2 pi f. 2 pi into 50, right? So what is dt? Anyone? 2
0.515.
0.515 seconds. Is it in seconds?
Yes, sir.
Fine. So this is your dt. You know what is dv. So C dv by dt mein, you know what is dv and you know what is dt. And you of course know that is equal to V naught by R. R has been given as 200 ohms in the question, right? 200 ohms in the question. And you don't know what is V naught, right? So V naught is changing from Vm to 0.95 Vm. So we can consider the average value, right? So what is the average? Average V naught is Vm plus 0.95 Vm by 2. Okay. So what is this? 1.95 by 2. So what is 1.95 by 2? 0.975 Vm. Correct. So what did we tell? Capacitor current is V naught by R is equated with C dV by dt. Okay. So that is equal to what? 0.975 Vm divided by R is 200 ohm is equal to C into dV is 0.05 Vm divided by dt is 0.515. Okay. So what is C? From here you can find out what is C, right? So 0.975 divided by 200. Yeah, so it will be some, it will be somewhere around 50.2.
0.05.
Yeah, so 0.05 or 50.2 millifarad. Okay, so I'll just check what these people are obtaining. So there is a discrepancy. So what mistake did we do? Maybe two. Okay. Okay. So okay, so we did a mistake in conversion of the angle to time scale. So you know what is dt, right? So the angle is pi by 2 plus alpha. That was the angle that we had got, 161.2. So how do you convert it into time? You need to multiply into t by 2 pi, right? So that is what we forgot to do. Correct. So into t by 2 pi you need to do, right? So angle 2, you if you need to multiply make it into time. So if you do that, that is 161.8 into capital T. Capital T is 20 milliseconds, so 0.02 divided by 360. Okay, so angle to time is your angle theta into whatever is your fundamental capital period divided by 2 pi. This will give you the time, right? So we should have done this. So 161.8 into capital T 0.02 20 millisecond divided by 360 degrees. Yeah, so if you do that, everything else is same, 0.975 Vm and 0.05 Vm, 200 ohms. So if you do that, you will end up with 876 microfarads. Okay, any doubts over here? We just needed to convert the time to angle to time properly. So any doubts? Yeah, so I'll just change. So this was not 0.515, this is going to be 161.8 divided by 360 into 20 milliseconds, 0.02. So if you do that, you will end up with somewhere around 860 microfarad. Okay. Yeah, and one more thing was, this is in degrees, right? So this is in degrees, but however, omega t is a quantity that is in radians. Okay, so first 161.8 needs to be converted to radians, and then only you can do omega t equal to this much radians. Therefore, t is equal to this much radians by omega. You got it right? So if you convert 161.8 into radians, so it will be 161.8 into pi by 180. So this much radians. So if you do it now, you will get the correct value of dt. Okay. So can anyone do this into pi by 180? So it will be somewhere around 0.00894. Okay, so you substitute that over here, 0.00894, you will get the answer. 0.975 divided by 200 into 0.00894. Yes, you are getting it. So you are getting around 870. You are getting around 870 microfarad. Correct. So you cannot directly apply degrees. You cannot write omega t in terms of degrees. Omega t is in terms of radians. So 161.8 into pi by 180 to convert into radians. That divided by whatever is the omega, that is 2 pi into 50. You understood, right? This question, any doubts in this question, or you want to revisit this question, you can tell me. Okay. So the ripple part is given. We calculated the discharge time in the previous question. You know that during the discharge period, your capacitor will deliver to the load. So load current equal to capacitor current. So V naught by R equal to C dV by dt. dV you know, dt you know. Convert the degrees to radians and radians into time, right? And then V naught by R. So calculate what is V naught, and you find out what is the capacitance required. Okay. Yeah. Yeah, 876.45 microfarad. Okay, so last question. A three-phase diode-based rectifier supplies a highly inductive load such that the average load current is 60 amperes. Peak ripple current is negligible. Determine the peak inverse voltage of the diode if the line to neutral voltage is 120 volt at 60 hertz. Okay, so line to neutral or the phase voltage is 120 volt. So is this RMS or peak? So anyone, is this RMS peak 120 volts?
RMS.
value.
Correct. So this is RMS. So if you want to find out what is peak, you need to do 120 into root 2, right? So this is your phase maximum. So what is your line to line maximum? It will be into root 3 of this, right? So 120 root 2 into root 3, right? Or 120 root 6 volts will be the line to line maximum. So now you can tell what is the peak inverse voltage. So peak inverse voltage in such a connection is basically line to line maximum, correct? So 120 root 6. So what is 120 root 6? Somewhere around,
293.93.
correct. So 293.93 volts. So the answer is yes, 294 volts. Okay. Yeah, so this is the correct answer. And we just saw this question in the first. So we have completed today's. Yeah, so any doubts so far? Or I think time is up, but anyway, any doubts so far in any of these questions? Were you able to understand all of them? If you have any doubts, please do go ahead and ask. I'll just pause for a minute or else we can close for the day.
So in question number 13, can you please repeat how to calculate V naught?
Question number 13. Yeah, so V naught is simply the average value. Okay. So see your over, so V naught, your, the profile of V naught is going to be something like this, right? Yes. So during the discharge period, it V naught is changing from Vm to 0.95 Vm. So we simply take the average of this. So that is why I have taken the average. V naught is Vm plus 0.95 Vm by 2. Simply the average only. Okay, 0.975 Vm. Okay. Any other question? Okay, so if you don't have any doubt, we can end for the day. Thank you everyone for attending. Have a great week ahead. And yeah, so we can close. Bye everyone. Good night. Yeah, thank you. Ishan.
Thank you so much.
Yeah, bye everyone. Good night.